Hello students, good morning. For the last two previous classes, we have been discussing superconductors, their properties and their advantages. We discussed that a superconductor material with zero resistance is a perfect diamagnetic substance, and the condition is it should be cooled to very low temperature called critical temperature. Below the critical temperature only, it is a perfect diamagnetic substance. And how could you say that the superconductor material exhibits diamagnetism below the critical temperature? It repels the magnetic flux. It does not allow the magnetic lines of force to enter in it. Then, also we discuss the applications of superconductor materials. They are used to prepare electromagnets, strong electromagnets. Also, they are used as the storage devices of magnetic flux. Magnetic flux is stored in the superconductor material. And the question is, if the superconductor material is a perfect diamagnetic substance below its critical temperature, even though it possesses zero resistance and free flow of current is there, then how could we use the superconductor material as a storage device of magnetic flux? How it is used in various electronic and electrical devices where we apply electrical and magnetic field. So this is our question, and today's topic is about the behavior of a superconductor material in the magnetic field, which is Meisner effect. Meisner effect is the answer for our question, and it describes the behavior of superconductor material at very low temperature in an external magnetic field. In 1933, German physicist Meisner explained the behavior of a superconductor material at low temperatures when it is placed in a strong external magnetic field. So to explain this Meisner effect, we choose a superconductor material like helium, cadmium, or you can choose a mercury. And also we compare the characteristics of the superconductor material with the ordinary material also, ordinary conductor also. So here we choose two materials. One is ordinary conductor, the second one is a superconductor material. And we observe the resistance of both ordinary material, ordinary conductor and a superconductor material. So we observed that at room temperature, ordinary conductor like iron, nickel and copper, they have small resistance. The resistance is not equals to 0. Even for superconductor material, the resistance is not equals to 0. Superconductor material and an ordinary conductor both have the resistance. Then what about the resistance of both materials below the critical temperature? The both materials are cooled to very low temperature below the temperature of critical temperature of the given superconductor, and observed that ordinary conductor like iron and nickel, they do not lose their resistance. They possess the resistance even at very low temperatures. But what about the superconductor material? A superconductor material below its critical temperature having zero resistance and current flows freely through it without any obstruction, and also it is a perfect diamagnetic substance. Then how could we prove that a superconductor material is a diamagnetic substance below the critical temperature? So an experiment done by Meisner. Meisner effect is the answer. For that, ordinary conductor material and a superconductor material both are placed in the magnetic field. At room temperature, observe the magnetic field passing through the both conductors. What is the magnetic flux passing through the both materials? Here we have the diagram. At room temperature, both the materials allow the magnetic lines to pass through them. Magnetic flux passes through the both materials. And what about the magnetic flux passing through the materials if they are cooled? Now cool the temperature, cool the two materials below the critical temperature. When both are cooling, on cooling, we observe that magnetic flux still passes through the ordinary material because there is no change in the behavior of ordinary material. Whereas superconductor material is a perfect diamagnetic substance, we can observe clearly in the diagram that a superconductor material below the critical temperature throws away the magnetic lines of force. Magnetic flux is thrown out by the superconductor material. No magnetic line of force is passing through the material. So magnetic flux is zero inside the superconductor material below the critical temperature. This is the difference between an ordinary conductor and a superconductor material. An ordinary conductor behaves the same even at a room temperature and a critical temperature. Even at both temperatures, the magnetic flux is passing through the ordinary material. But for a superconductor material, the magnetic flux passes through only at high temperature. When the temperature is decreased below the critical temperature, it becomes a diamagnetic substance. At that below temperature, critical temperature only, it is a diamagnetic substance. This is the reason why it throws out the magnetic flux. So the reason for the magnetic flux thrown out is ordinary conductor is not a superconductor. It does not exhibit the superconductivity, whereas a superconductor material is a perfect diamagnetic substance with zero resistance. So then the question is, if it is a perfect diamagnetic substance, then how could we use this as a storage device of magnetic field? How it is used in all electrical and electronic devices where electromagnetic field is applied. So the answer is here. The superconductor material is selected in an anchor ring shape. So this is the shape of the superconductor material, which has the outer edge and inner edge at the center. When it is placed in a magnetic field, a strong magnetic field, magnetic flux passes through the material, and magnetic flux passes through at the inner edge, inside the center, and at the outer edge also. When it is cooled to the below critical temperature, the flux or the lines of force passing through the material at the inner edge will not be thrown away. They are still linked with the material, whereas at the outer edge the lines are thrown out. If the field is switched off, then lines of force are absent at the outer edge, but within the inner edge magnetic lines settle at the inner edge, and now it is used. It can be used as storage device of magnetic flux. So students, this is about the Meisner effect, which describes the behavior of superconductor material and how could we use a superconductor material as the storage device of magnetic flux. And also this Meisner effect describes the types of superconductor materials, type 1 and type 2. So we will discuss the classification of superconductor materials in the next class.